and a fourth for the validation and a fourth for the testing or something like that. And you pull those values out of your whole set at random. And then if you want to go through the whole thing again and pull out new random sets, and that mixes everything up just in case you happen to get a bunch of weird ones in one data set and not the other. Okay, so then they took their neural network and they applied it to chlorophyll imagery from sea whiffs in the Gulf of Maine. So Cape Cod, we're up here, Nova Scotia. Okay, so here's chlorophyll in the Gulf of Maine generated by applying the neural network to the sea whiffs data. Here's what they got. Then here's the difference in the neural network and the sea whiffs OC4 algorithm retrieving chlorophyll. So if it's this kind of greenish color here, that's really not much different. So there's a fair bit of area here where they basically gave the same answer. But you'll notice the dark blue, that's where the answers, the neural network is less than the OC4 algorithm. So that's a negative number by like minus 1.5 or 2 milligrams per cubic meter. And you see that's happening mostly right along the coastal area where what's in the water out here, a lot of extra CDOM. And that OC4 algorithm was really for open ocean case 1 water, so it put out a bad value for those high CDOM coastal waters. No surprise there. And the neural network, on the other hand, it seemed to do pretty well there, and it gave different answers right where you expected it. And the black here and here, those are clouds, and then that's land. So anyway, that's the story. They did this comparison here, and I guess I guess they didn't show I didn't show the results here. But anyway, the neural network did considerably better than the canned band ratio algorithm, especially along the coastal waters, which are really difficult for those band ratio algorithms. Okay, if this gets you all excited, Emmanuel found a website I wasn't aware of. It's called 3 Blue 1 Brown. So www.3blue1brown.com. It's some guy who has put all of these videos up of all kinds of mathematics and physics things. And he's got a really nice example where he shows how to train a neural network to recognize handwritten numbers. So he's got a 28 by 28 pixel grid here. And so you're going to write into this grid 3, or maybe your handwriting's kind of crappy, or your handwriting is like that. So you're simply going to write a bunch of 3s on this. 28 by 28 is 784 pixels. So he just unwraps these, and he has an input layer of 784 values. And the values are, it's anywhere from 0 if there's nothing written, up to 1 if it's a pixel where you wrote on it. Or maybe in between it's kind of a little gray, so maybe it'll input a half or something. But anyway, the value from each pixel simply goes in to here. 0, 0, 0, oh, we hit this point, now it's a 1. Then he's got 2 hidden layers of 16, and the output layer is simply, there's 10 of them, which are 0 to 9. So he goes through the whole business, this neural network of, by putting in lots and lots of examples of people's handwriting and saying, okay, these are 3s, and then it comes along and he puts in lots of 4s, and he puts in, some kind of thing like that, but he keeps telling them, these are 4s, these are 3s. The neural network eventually comes up with weights, so if it sees this, it outputs that that's a 3. And it's amazing how well this stuff works. So you can go there, go to that website, and he's got all kinds of things. This is one of, there's actually about 4 videos here that are like 20 minutes long each. Setting it up, doing the training, what's really going on behind the scenes, etc. So it's a nice website. Okay, so the take-home messages here. are that these statistical methods, they've been really, really successful. They're widely used. You have to keep in mind they're all based upon data sets. One way or another, you're using some data set to train this thing, whether it's a simple band ratio or it's a really fancy neural network. And so your algorithms, once you get them, are only going to be as good as your underlying data that were used to fix these parameters. And this, of course, ties the algorithm often to a specific time or place. So if you tuned your neural network with data from the North Atlantic, don't expect it to work so well in Antarctica. If you tuned it with data from the Yellow Sea in the summer, it may not work so good in the Yellow Sea in winter. And that's just always the case for any kind of statistical model. And a philosophical disadvantage is they sort of obscure the underlying biology or physics. You don't know which wavelengths or why certain wavelengths were more important at determining chlorophyll and others were more important at determining, KD at 490. You could maybe kind of figure it out. But if you have a really complicated neural network like this, you can't sit down and say, oh yeah, this weight here is a certain value and this one's a certain value and that's a certain value and that's why I got a 3. I mean, it's just way too complicated to do that. Okay, and that's not a criticism. It's, if what you're interested in is getting the right answer, they work pretty well. So band ratio algorithms have now been around since the very first days of ocean color remote sensing. Intellectually, there's kind of nothing more to do. People keep getting new data sets. They come up with a new algorithm that works for the Arctic Ocean in the summer or whatever it is. Well, that's fine. They can now do a better retrieval for the Arctic Ocean in the summer than if they were using one that was based on North Atlantic data, or Mid-Atlantic data. But intellectually, I don't see anything really new to be done there. You're just kind of getting better and better at what you've already been doing. And on the other hand, they're very successful. They work great. Still, things like VIIRS and so forth are still using band ratio algorithms. Okay, so here's my story. Down in the Grand Canyon, and I found this amazingly beautiful rock, which is about like this big. It's down by the river. It's just been polished, glassy smooth. And up above you, there's a cliff of what's called the Muav limestone, which is this gray limestone. It's sort of early Cambrian period, roughly 500 million years old. So a piece of that had tumbled down, gotten polished by the river. And what was so cool is it has these red streaks in it. And according to the geologists, those are actually fossilized algal mats. The rest of the gray stuff is just basically sediment that's been turned into rock. But these are algae. And you get that by take a rock sample here and one here, and they have slightly different ratios of carbon to oxygen to phosphorus to nitrogen, etc. And there are, living organisms have certain ratios of those chemicals to each other, whereas non-living things don't. So they've figured out that, these were actually just, blobs of scum on the bottom of some water body at 10 meters down or 5 meters down, and now they're fossilized algal mats. So I thought that was really cool to see something like that in this rock. Now, I wasn't really down there looking for rocks. I was rafting the river, which I've done a couple of times. So here's going through lava falls. I'm on shore taking a picture of one of the boats going through. Lava Falls is considered the biggest runnable rapid in North America. It's a class 6 rapid. Class 7 means you die. And class 1 is like level water. So anyway, we've got these rafts. We're on a trip that I think it was 17 days long. So they're pretty well loaded down with gear and people. And they're heavy enough that in the rapid, there's these huge standing waves that are like 3 or 4 meters high. And so here we're going in. They're kind of going down in a hole with this big standing wave here curling over them. Well, the rafts are so heavy, they don't ride up and over the waves, they bury through the waves. So they're going in here, diving, they're completely underwater, coming out the other side, and there they are. You still count heads, yeah, 1, 2, 3, 4, 5, whatever. There's not always the same number, it's always less. And then right after this, in about 2 seconds, you hit Dead Man's Rock, and you have to make this sharp left turn, and it drops down like another 10 meters in elevation, and you get down here and you're home free. The cool thing is that on Dead Man's Rock, like about 20 feet, maybe 6 or 7 meters down, there's a hole about this big around that goes all the way through the rock. And when you go around the backside where it's calm water and you can look down and you can see the light coming out that hole. And there's been at least one person I know of came out of the raft, went underwater, and got sucked through the hole with minor cuts and scrapes. So anyway, rafting the Grand Canyon is the trip of a lifetime that you should do every year. That's all I can say. And I was leading Sierra Club trips back in those days, so this was a Sierra Club trip. So that's my story. Colin, you're up next. You can take it from here. And